Welcome to Center of Math's Complex Analysis Basics series. Today we're going to talk a little bit about the residue theorem. So the residue theorem is a very useful way to integrate functions. And so something we should talk about first, a regular point is a point of a function if at a certain value we can at a certain point in the complex plane, we can give that function a value such that the function becomes analytical around that point. And it's originally not defined at that point, but we give a value, it becomes analytical around the point. That point's a regular point. Points that are not regular points, they are singular points. And we're interested in the singular points for the residue theorem. So around a singular point, we can write a Laurent series for our functions, saying it's analytical in a deleted neighborhood of a point, say z naught. And so by the residue at z naught, we mean the coefficient of a minus 1 in the Laurent expansion of this deleted neighborhood of this point. So if we have a singular point, z naught, and we say in a deleted neighborhood of the singular point, we have a Laurent series, so it's analytical in the deleted neighborhood. So by the residue at z naught, we mean the coefficient a minus 1 in the Laurent expansion. So the coefficient of 1 over z minus z naught. And the residue theorem is a simple theorem. It states that given some contour integral, f of z dz, the integral is just equal to 2 pi I times the sum of the residues of the complex function at its isolated singular points. And to prove this is not actually too complicated. So let's say we have some contour integral of some function f of z dz around some closed loop in the complex plane. So by Cauchy's integral theorem, we can think of this, since we know if f of z is completely analytical in a domain, we have a contour integral in that domain, interior contained in it, it's all contained in it, the integral will just be 0. And so by Cauchy's integral theorem, we can really calculate the integral we want by just a bunch of circles, arbitrarily small circles around our isolated singular points. And so really, in this integral, we're just going to look at one of these circles around one of our singular points and try to calculate what its value is. And so writing it as saying we have a deleted neighborhood of our isolated singular point, our circle is small enough so it's analytical in the circle except for the point we're looking at. So we write a Laurent series for our function. We pull out the summation sign, and then we do a couple of further manipulations, and we'll see it simplifies quite a bit. So since we're integrating on a nice circle, where z minus z naught is just r e to the I theta, because it's a nice smooth circle we're integrating on. So plugging that in, we get r to the n e to the I theta n d r e to the I theta. And doing some algebraic moving things around, we get the sum from n goes from minus infinity to infinity, a n r to the n plus 1, and then integrating from 0 to 2 pi e to the I theta n plus 1 d theta. And so this integral here, we note that if n is not negative 1, this thing will just be 0. Yeah. And so we want, so the only value it's not going to be 0 for is n equals negative 1. So plugging in n equals negative 1 here, we see we no longer need to deal with this infinite sum. This becomes just 2 pi. 2 pi I. And so, yeah, 2 pi I. And so this just becomes 2 pi I a to the minus 1. And so this is, so yeah, 2 pi I a to the minus 1 is the contour integral of one of our circles. And so our total integral is just the sum of all these circles. And so adding them up, we get that our total integral, the integral in some arbitrary contour, it's just equal to 2 pi I times the sum of all of our a minus 1s of our Laurent series around these singular points. But that's just the residue theorem. And so we conclude that we in fact have the residue theorem. Yeah, that proves it. Thanks for watching. If you like these, please check out our other videos in the complex basic series. Thanks for watching.